Hi, welcome back. All right, so the last video ended, we had found x in degrees. That's the measure of that arc. But Dominic wants to know if angles A and B have the same degree measure. So if you look at the picture, angle A is a central angle, so it equals its arc measurement. So the measure of angle A is 45 degrees. All right, now we are going to do the same thing with circle 2. So we're going to take the arc length, 13 pi over 8, and that is going to equal, now I'm going to call the measure of this arc in degrees, y degrees over 360 times 2 times pi times the radius, which is 6.5. So again, I'm multiplying two fractions. So you multiply numerators. So I'm just going to be doing y times 2 times pi times 6.5. So pretty much I'm just doing 6.5 times 2. 6.5 times 2 is 13. So I'm just going to rearrange. I have a 13. I still have my pi. I still have y, and that's over 360. Now I'm going to cross multiply. So 13 times 360 is 4,680. And we still have our pi. And then 8 times 13 is 104. That's 104 pi times y. So again, pi is on both sides of the equal sign. I could divide it out. So I have 4680 equals 104y. Divide both sides by 104. 4680 divided by 104 gives me 45. So again, the measure of this arc is 45 degrees. Angle B is a central angle. So the measure of angle B is equal to the measure of the arc. So Dominic is correct. Both angles equals 45 degrees. That was a little sloppy. All right, so that is that question. And like I said, that was on a Regents exam 1 year. All right. Let's talk area of a circle. Area of a circle is the amount of two-dimensional space inside a circle. The formula is on the reference sheet, pi r squared. Now, I would like to define a sector of a circle. Is a region bound by an arc of the circle and two radii to the arc's endpoints. You name a sector using one arc endpoint, the center of the circle, and the other arc endpoint. Kind of like an angle, but there's no symbol for sector, so this you would just call it sector XOY or sector YOX. So it looks like a slice of pizza, a slice of pie, so that is a sector of a circle. So if we wanted to find the area of a sector, again, we don't want the area of the entire circle. We want the same fractional amount of the area of a circle. So area of a circle is on the reference sheet. So again, all you are really doing is memorizing that. The whole formula you need to know, but that part of it's on the reference sheet. All right, same thing as before. You're doing the same fractional amount, the measure of the arc in degrees. This is degrees divided by 360 degrees. The degrees cancel out. So the only units are what your radius is going to be in. And area is two-dimensional, so it'll be those units squared. So let's try an example. Find the area of sector ZOM. Leave your answer in terms of pi. So area is going to equal our degree measure. Here it is. Our degree measure, 72 degrees out of 360 degrees, times now the area, pi r squared. Leave your answer in terms of pi. So all I'm typing in is 72 divided by 360 times 20 squared. And that gives me 80. And this is 80. Leave your answer in terms of pi, and the units are centimeters, and since it's area, that would be squared. All right, let's try another one. In the diagram to the right of circle O, the area of sector AOC is 4 pi inches squared, find the measure of the arc. I'm going to label that x. That answer is going to be in degrees. So this is area. So they gave us the area, and that is going to equal our measurement in degrees out of 360 times pi, and then the radius squared. Again, this is all one, you're multiplying fractions, multiply numerators, multiply denominators. So x times pi times 12 squared. 12 squared is 144. Here's my pi, here's my x. It really doesn't matter what order they go in. They're all being multiplied together. I can turn the other side into a fraction and now cross multiply. 4 pi times 360. I just need 4 times 360. It's 1,440. Notice pi is on both sides, that you can divide it out of both, cancels out. So I have 144x equals 1,440. Divide both sides by 144. X gives you 10, and the label for that is degrees. The measure of the arc is 10 degrees. All right, so it's not that bad. It's not that hard to use. All right, a couple more. Triangle FGH is inscribed in circle O. Inscribed means it's completely inside. The length of radius OH is 6. Line segment FH is congruent to line segment OG. So I'm going to put my tick marks in there. What is the area of the sector formed by angle FOH? So we want the area of this sector here. Kind of lightly shading it in. So we want the area of all that. All right, so we need the radius, which we have, and we need the measure of this arc. 6 is the only number in the problem. So you need to be thinking. In this unit, you always have to look for things. Radius, 6. Are there more radii in this picture? Radii are something you need to look for. There's 2 more. There's a radius here, so that is also 6. There's a radius here, that is also 6. And since line segment OG is congruent to line segment FH, that is also 6. Does that help me find the measure of an arc? I don't know. Stare at this some more. Do you see a triangle here? What kind of triangle is that? It is equilateral. All 3 sides have the same length, which means all 3 angles are going to have the same measure. There's 180 degrees in a triangle. If all 3 of them are the same, they're all 60 degrees each. That is also now a central angle, so the measure of its arc is also going to be 60 degrees. So there you have it. So now we can set up our formula. Area is the measure of the arc divided by 360 degrees times pi times your radius squared. Do you notice all these have pi in it? So I'm not going to do anything with the pi button again. So 60 divided by 360 times 6 squared gives you 6. And the pi was still in there. There were no units in this problem. So 6 pi units squared. All right, last thing I want to talk about is the fact that all circles are similar. So recall, 2 figures are similar if there is a single or a sequence of transformations that could map one figure onto the other. So it is very easy to prove circle P is similar to circle Q. So a sequence of similarity transformations that would always work to establish 2 circles to be similar would be a translation vector. You're just going to translate one circle onto the other. And then a dilation. All right, so it's very easy to do. So I am going to connect the 2 centers, and I'm going to put an arrow. That is a vector. It gives you a specific length and a direction. All right, so let's describe what we're doing. First thing, we are going to translate circle P onto circle Q. Q along vector PQ. All right? So then you're going to have the smaller circle inside. Next thing is a dilation. So we are going to dilate circle P. With the dilation, you have to give two facts. You have to give the scale factor and you have to give the center of dilation. So we're going to dilate circle P using P as the center. P now is going to be Q, actually. P and Q are now the same point. And then with a scale factor of the larger radius is 5, smaller one is 2. And we moved the small one onto the big. So it's getting 2.5 times bigger, 5 halves, or 2.5. It's getting bigger, so your scale factor is greater than 1. So it's very easy to prove that all triangles are similar. You would just translate and then dilate. That's it. Pretty easy. All right, the last thing was for you to look at this and just note all the different items that you see. There's all sorts of items in there. If you want, you could check out my answer key online. These were all items I noticed. All kinds of things. All of this you can notice. E is the midpoint of line segment AB and line segment CD. These are all conclusions you can make. All kinds of things in there. And these are all things you need to see. You need to train your brain to notice all these different items in there. All right? So that's it for day 1. Have a great day. Bye.